Hello, this is the lecture on NP-completeness. We will first see what Turing machines are and what the complexity classes P and NP are. And then we'll see the basic notion of a reduction, and we'll see how to prove that the problem is NP-complete. And then we'll see a few examples of NP-complete problems and their NP-hardness proofs. Let's start from the very basics. So what is a polynomial time algorithm? We say that an algorithm has polynomial running time if there exists a constant c such that the worst case running time of the algorithm is of the order n to the power c, where n is the size of the input. So you know many polynomial time algorithms, and here are some of the running times you could encounter. If we have a running time that's linear, that means that the running time is order n. You could have running times of the form n squared log n. You could have an n cubed running time, or an n to the power 20, that's also still polynomial. And then we have super polynomial running times. So we have n to the log n as a super polynomial running time, and everything where the running time is asymptotically larger than polynomial is super polynomial, such that sub-exponential times like 2 to the square root n, or exponential times like 1.001 to the power n, 2 to the power n, n factorial, and so on. Okay, and now one of the central questions in computer science is which computational problems have polynomial time algorithms. And computer scientists early on have encountered an intriguing class of problems, the NP-complete problems. And unfortunately, it's not known whether NP-complete problems have polynomial time algorithms. And moreover, a polynomial time algorithm for one NP-complete problem would imply polynomial time algorithms for all problems in the class NP. So the class NP contains P. It also contains all the NP-complete problems. So the NP-complete problems can be thought of as the hardest problems in this class NP. Because if you could solve one of these NP-complete problems in polynomial time, you could solve then every problem in NP in polynomial time. Quite surprisingly, lots of problems fall into this class of NP-complete problems. Gerhard Wilginger has a very nice page on the P versus NP problem, and he lists many attempted proofs where they wanted to show either that P equals NP or that P is different from NP, because this is a very important problem that has a lot of prize money, and so people have been attacking this, but so far we don't know whether P is equal to NP, or whether indeed there are some problems in NP, in particular the NP-complete problems, where we need super polynomial running times. So at the moment we don't know polynomial time algorithms for these, and often the best known running times are exponential time. Let me give you a few examples of problems where just making a very small modification to the problem statement brings us from a polynomial time solvable problem to an NP-complete problem. So the first example is shortest path. So we're given a graph G and two vertices in this graph. Let's call them A and B. And we are also given a budget. So that's an integer k. And the question is whether there's a path in G from A to B of length at most k, so traversing at most k edges of the graph. So that's a simple polynomial time problem. You can solve it during Breadth first search, for example. But then we have on the other side, on the NP-completeness side, we have the longest path problem. And here we are given a graph G and an integer k. We are not given endpoints of the path, And the question is whether G has a simple path, so one that doesn't intersect itself, of length at least k. And so this problem is NP-complete. So finding a short path between two vertices is polynomial. Finding a long path in a graph is NP-complete. The next example is Euler tour. So given the graph G, does G have a cycle that traverses each edge of G exactly once? And here we can obviously intersect, the cycle is allowed to intersect itself. But can we make it such that each edge is traversed exactly once? So that's a polynomial time problem. On the other hand, we have the Hamiltonian cycle, which is given a graph G, does G have a simple cycle, so one that doesn't intersect itself, that visits each vertex of G? Since it doesn't intersect itself, it needs to visit each vertex of G exactly once. So these problem statements are quite similar, but one of them has a polynomial time algorithm, and the other problem is NP-complete. We have 2 CNF set and 3 CNF set, where for satisfiability we are usually given a formula, a Boolean formula, in conjunctive normal form. So we have variables that represent Boolean values, let's say 0 or 1, and then they are combined using a big AND, so a conjunction of clauses. And each clause is a disjunction, so an OR, of let's say k, at most k literals. And the literal is one of these Boolean variables or its negation. So we have a big AND of clauses. Each clause is a disjunction, an OR of at most k literals. And then we have a KCNF formula. So the satisfiability problem is to check whether a formula in CNF that's given as an input can be satisfied. So can we set the Boolean variables in such a way that the formula is satisfied? And we speak of KCNF set if we have a KCNF formula in the input, so where the clause length is bounded. And 2 CNF set is polynomial time solvable, whereas 3 CNF set is NP-complete. Other examples are 2 coloring is polynomial, 3 coloring is NP-complete. So you see that just from looking at the problem statement, it's not really easy to guess whether a problem is polynomial time solvable or NP-complete. Okay, so what's next? So we will formally define the classes, the complexity classes P, NP, and NP-complete. And we learn a new skill, or for some of you it's new, for others of you might already have this skill, which is to show that the problem is NP-complete. Okay, so to make things formal, we need to say what problems we are interested in and what problems these classes contain. So we'll only speak in this lecture about decision problems, so which is a problem that has always a yes-no answer. So instead of computing let's say, a smallest vertex cover of an input graph, we'll have a similar problem that says, okay, given an input graph G and an integer k, is there a vertex cover of size at most k? So that we make a yes-no question out of the problem. Okay, so a decision problem has a name. It has an input, which is the instance that any algorithm that is supposed to solve this problem is given. And there's also a question, which is a yes-no question. And since we are talking about running times, we need to somehow make a bit clear how this input is given. Because I could have like several encodings of, let's say, a graph or of an integer. I could, for example, encode an integer in binary or in unary. If I encode it in unary, of course, I waste a lot of space, so it's much more efficient to encode integers in binary. And we'll assume that the input that we are given doesn't waste space. So we are always assuming that we get a reasonable encoding of the input. And so, for example, for a graph that has n vertices and m edges, we will say that well, the input size is n plus m, or of the order n plus m. Many encodings are polynomial time equivalent because, so here in this lecture we want to know what can be computed in polynomial time, and so often it's not really crucial how exactly the input is given, because several encodings of the same thing can be translated to each other in polynomial time. There's the important exception, of course, of the unary versus binary encoding of integers. So to encode an integer x takes log x bits in binary, but 2 to the power this in unary. So we'll assume a binary encoding of integers. We can view decision problems as languages. So notice that our input is encoded in some way. And let's say that we used symbols, the set of symbols sigma. And so we call this set of symbols the alphabet. Without loss of generality, we can always assume that the alphabet is 0 and 1. And now a language over this alphabet is just a set of strings made with symbols from the alphabet. Okay, so since we are looking at decision problems, we can now take all of the strings that correspond to yes instances, so for instances for which the answer is yes, and so this set of strings is now a language. So after having fixed an encoding of our instances into this alphabet, we can now define a language that corresponds to the problem. So, and the language that corresponds to the problem is basically the dictionary of all the yes instances for the problem. For this problem pi, we have that x is a yes instance for pi if and only if x is in this language. Let us now define Turing machines. There are deterministic Turing machines and non-deterministic Turing machines. So I define here the most general ones, which are the non-deterministic ones. Deterministic Turing machines are special cases. The Turing machine has a memory, which is an infinite tape. And this tape has cells, and our input word, so the input, is written on the tape. So each cell of the tape contains exactly one symbol of the input word. And the Turing machine also has a head. And the head is placed on one symbol of the tape. And it also has, the Turing machine also has states. And there's a start state, and so there's several states. Below here we have an example. So here's the tape. It contains symbols. The arrow represents the location of the head. The vertices here are states. There's some special states, like this is an accepting state. And then the arrows, or the directed edges, they represent transitions. So they tell us what possible transitions there are. And we also have a start state. So this state here would be the start state. Okay, so let's look at this example. What's happening here? So the head is placed on one symbol, let's say we are in the start state here. And now the transition tells us, well, if we are in this state and we read a 0, then what we do, the arrow tells us in which state we transition. This tells us which symbol we write on the current where we are currently placed, and this tells us whether we move the head left or right. So in this example, if we're in this state and we read a 0, then this transition function allows us to write a 0, move the head right, and stay in the same state. Okay, so what would happen here now that the head would just move one position to the right, and then what would it do then? Well, it's still in the same state. So now if we read a 1, and the transition function tells us that we can now move to the other state here, the blue state. We write a 0 and we move the head to the right. So what would happen here is we replace this 1 by a 0 and we move the head to the right. If we now read another 0, then while we stay in the state, we write the 0 and we move right. If instead we actually read a 1, we move to the left state, we write a 0 and we move to the right. So this little example machine here, it will keep moving to the right. The only possibility where it can move to the left is when it reads this symbol here. So it's defined here, so that's a blank symbol. So initially we assume that all the cells of the tape are blank except where the input word is written. So basically the machine will move to the right, do some transition into states, replace everything it reads by a 0, and now when it has reached the last symbol of the input word, what will it do? So now when it moves to the right, it will read a blank symbol, it will write a blank symbol and move to the left and now transition into this state H. And the state H is one of these accepting states. So these are usually depicted by a double circle. So these are the accepting states. And now now there's no transitions anymore, right? Once it is in this accepting state, there's no transition, so it has finished its job. If instead, so that's one possibility. So it could end up in this accepting state, but it could also be that it keeps going to the right, and now it is in this blue state here when it reads the blank symbol. And there's no transition for this. So this means that now it stops and it has finished its job and it has ended up in a state that's not an accepting state. So what does this little Turing machine actually do? Well, it starts in some state. As long as it reads a 0, it stays in that state. If it reads a 1, it toggles to the blue state. If it reads another 1, it toggles to the left state again. If in the blue state it reads a 0, it stays in that state. So if it reads a 0, it stays in the state it is. If it reads a 1, it toggles the state. So basically, after having read an even number of 1s, it will be in the left state. After having read an odd number of 1s, it will be in the right state. And now when it reads the blank state, if in the end it has read an even number of 1s and it reads a blank symbol, then it will accept, otherwise it will not accept. Okay, so that's what this machine does. It just allows us to tell whether the input word has an even number of 1s, because that's the only case where it will accept. Okay, so more formally, So our Turing machine will have a set of states. It will have, it can work with some symbols. So these are all the symbols it can work with. The input symbols might be a subset of this. Actually, this here, that should be the blank symbol. It shouldn't be a B. We also have a start state that we define because, well, the machine has to start in some state. And we have this transition function. Okay, let's talk a bit more about this transition. Actually, it's not a function here. It's a transition relation. If it were a function, that would actually make it a deterministic Turing machine. And this machine here that we had on the left, that is actually a deterministic Turing machine. Why is it deterministic? Well, when the machine is in some state and it reads a symbol, there's only one transition. There's only one thing it can do at most. So for each state, there's at most one outgoing directed edge for each symbol that it reads. So if it is in some state and it reads a 0, there's only one transition that it can do, or at most one. But in general, this transition relation could be an actual relation. So there could be multiple directed edges that are possible when the machine is in some state and it reads a given symbol. So if there's multiple possibilities, multiple transitions it can perform, possibly, then this is a transition relation, and now we have a non-deterministic Turing machine. Okay, so what does it mean now for a machine to accept something, because we don't know actually what it does, because there's multiple things it could do. Well, we say that a non-deterministic Turing machine accepts an input word if it is possible for it to arrive at a halting state that is an accepting state. So that's the big difference between deterministic Turing machines and non-deterministic Turing machines. For deterministic Turing machines, it is predetermined how it works on a given input word. For non-deterministic Turing machines, the machine can basically transition into multiple possible worlds. It can explore multiple possibilities kind of in parallel, non-deterministically. Another way to see this is it could make optimal guesses. So it guesses in which transition to use, and we assume that it made an optimal choice each time, so that it can actually arrive at an accepting state in the end. So we will say that a non-deterministic Turing machine accepts a word X if there exists a sequence of computation steps starting in the start state and ending in an accept state. And the language accepted by a non-deterministic Turing machine is the set of words it accepts. Since deterministic Turing machines are special cases of this, these definitions can be easily extended to deterministic Turing machines. Okay, so we'll say that a language is accepted in polynomial time by a non-deterministic Turing machine M if, first of all, L is accepted by M. So M accepts each word in L, and there's a constant K such that for any word in L, the non-deterministic Turing machine accepts this word in order cardinality of x to the power k computation steps. And a computation step is exactly one of these transitions. We have already talked a bit about deterministic Turing machines. So those are non-deterministic Turing machines where the transition relation contains at most one tuple of the form where the first element is s comma a for each state and symbol. Okay, so if we're in a given state and we read a given symbol, there's only one transition it can do. So that's what this means. And therefore we can now view the transition relation as a function, which is basically a function that for a given state and symbol gives us what we should do. So it gives us the new state, the symbol it should write, and whether to transition left or right. Now, for a given input word x, there exists exactly one sequence of computation steps starting in the start state. If we have a deterministic Turing machine. So there's no choice that the machine can do. It is forced to follow the transitions that are defined in the transition function. Okay, now there are a lot of models of computation that are equivalent to deterministic Turing machines if we talk about polynomial time computation. So it means that what one of these models of computation can compute in polynomial time can also be done by the other one in polynomial time. So one of them is the random access machine that's used for algorithms in many textbooks. And others are variants of Turing machines, like Turing machines with multiple tapes, Turing machines where the tape is infinite only in one direction, but not the other one. So those are all equivalent. Let's now define P, NP, and co-NP. Okay, so P, what is it? So we know already P is a set of decision problems. So it's a set of problems, and we define P as the set of decision problems, so those languages, such that there's a deterministic Turing machine that accepts this language in polynomial time. So basically, when we get an input that's a yes instance, the Turing machine does its computation steps, and it ends up in an accepting state in polynomial time if we were actually given a yes instance. If we were given a no instance, it does not end up in an accepting state. Now, NP, so that's the set of languages such that there exists a non-deterministic Turing machine that accepts L in polynomial time. So it's the same as P, except that we have access to this non-determinism. So the Turing machine now can do guesses, basically. It can guess which one is the optimal transition I should use for ending up in one of these accepting states. Okay, so what is co-NP? Well, it's the complement. So if a language is in NP, then the complement is in co-NP. So basically, it's the no instances of a problem in NP. Okay, so now would it make sense to talk about co-P? Well, actually not. So if we have a language in P, then we know that there exists a polynomial time deterministic Turing machine that holds in an accepting state on every word in the language, and it holds in a non-accepting state on every word that's not in the language. So basically, co-P is equal to P. So it doesn't really make sense to talk about co-P. So in terms of NP and co-NP, these are actually different. Assuming that P is not equal to NP, of course. Okay, let's try and prove this theorem 8. So suppose we have a language in P. Now, by the definition of P, Now there must exist a deterministic Turing machine, M, that accepts this language in polynomial time. And so basically what we need to do is we need to find a deterministic Turing machine, M prime, that simulates M for a polynomial number of computation steps. And this is the running time of the machine M. And now this deterministic Turing machine M prime, it will simulate M for this many steps and then transition into a non-accepting state if M does not hold in an accepting state. So basically it simulates M, and now basically it watches what M does, and if M goes into a accepting state, our machine M prime goes into a non-accepting state, and vice versa. But okay, so we know that, so one can show that this simulation can be done with only a polynomial overhead, and therefore we can design such a deterministic Turing machine M prime that does the simulation and then basically does the opposite from what M would do. But note that this proof is actually non-constructive. So by non-constructive I mean that even if we have access to this deterministic Turing machine M, building M prime requires us to know how many computation steps M uses at most. But we might actually not know this exactly, precisely, so therefore this proof is non-constructive. But so what we proved here is that M prime exists, but we didn't give an explicit way of constructing M prime from M, because this C times N to the K, well, for this to actually work precisely, we would need to know what C is and what K is. And we might not easily be able to find this out from just the description of M. Okay, so let's get back to NP. So these non-deterministic Turing machines, they basically make guesses. So if they have multiple transition functions or multiple transitions that they could follow, they make a guess of which one to follow, and then we always assume that they made the right guess. If we wanted to, let's say, simulate a non-deterministic Turing machine by a deterministic Turing machine, or by some other deterministic model of computation, then basically we would need probably to explore all these guesses and all possibilities for these guesses. What if we knew this guess, the guess that the NP or the non-deterministic Turing machine makes? So if we know exactly that, well, if the non-deterministic Turing machine has several options, then if we know what guess it makes each time, then we know everything, right? So then we know everything, and we can then check whether these guesses lead to an accepting state in polynomial time. Okay, so an encoding of these non-deterministic choices gives us a kind of certificate. So if we know these non-deterministic choices, we can now simulate the deterministic Turing machine, and now, given the input and the certificate, we can verify that actually, yes, this input word X is in the language. Okay, so basically, if we know this certificate, we can do everything in polynomial time, but of course, we might not know this certificate. But this gives us now a different definition for NP. So we can say that language L is an NP if and only if there exists a deterministic Turing machine V, so that's the verifier, and for each input word, x in L, there exists a polynomial length certificate. Why is it polynomial length? Well, it's the non-deterministic Turing machine took only polynomial time, right? So it made only a polynomial number of guesses. Okay. So L is in NP if and only if there's a deterministic Turing machine V, and for each input word there exists a polynomial length certificate C, such that if we hand x and c to V, then it returns 1. But if we hand some word to V that's not in the language L, and together with some other certificate, then it will return 0 for each y that's not in L. Okay. So if we're given the word in L, then now we say that there exists a certificate of polynomial size such that the verifier V returns 1, but the verifier V does not return 1, or it returns 0 for each word that it shouldn't accept. So basically this gives us a like a guess and check procedure for NP. So there's a process that makes guesses. So it guesses the certificate, and now in polynomial time the verifier is able to check whether or not the certificate works for this instance. Let's talk about one of the most important problems in NP, CNF satisfiability. So a CNF formula is a propositional formula in conjunctive normal form. So it contains a conjunction, an AND, of clauses. Each clause is a disjunction, an OR of literals, and each literal is a negated or unnegated Boolean variable. So in the example here, we have 3 clauses. First clause contains x, not y, and z. The second one contains not x and z. And the third one contains not y and not z. Now, an assignment is, well, a function that goes from the variables of the formula to 0 and 1. And so it sets each variable to 0 or 1. And now we say that the clause is satisfied if, well, the clause contains at least one true literal. And we say that the formula is satisfied if each clause of the formula is satisfied by this assignment. Okay, now the CNF set problem has as input a CNF formula f, and the question is whether f has a satisfying assignment. So is it possible to find a setting of the Boolean variables to 0 and 1 such that the whole formula is satisfied, or the whole formula becomes true? Okay, there's a lemma here that says that CNF set is in NP. So why is that? Well, to prove this, we would need to define a non-deterministic Turing machine that actually solves this problem. And so let's just think about this abstractly. We are not going to write an actual Turing machine. But so we can encode this formula, and so what can the Turing machine do? So it can check, or first of all, it can guess the assignment. So it can guess some assignment of the variables, and let's assume that it made the correct guess. Now the only other thing that it needs to do, it needs to check that actually these guesses that it made satisfy the formula. And this is easy to do, right? Maybe not by writing a Turing machine, but since Turing machines or deterministic Turing machines are equivalent to other models of computation, we can easily write an algorithm or a pseudocode algorithm that checks that actually a given assignment is a satisfying assignment for a given formula. And since we can do this in polynomial time, and since the length of the certificate, so the encoding of such an assignment, is polynomial, we then get that CNF set is in NP. Okay. So the proof is just we need to define what the certificate is. The certificate is an assignment to the variables, and we can easily convince ourselves that encoding such an assignment has polynomial length. And now, given the certificate, it can be checked in polynomial time whether all clauses are satisfied. So that's all we need to do to show that the problem is in NP. So we define what the certificate is, and then we give a simple algorithm or simple reasoning why it's possible to check the validity of this certificate in polynomial time. Okay, our next theorem gives us a brute force way to solve every problem in NP based on these certificates. So it says that every problem in NP can be solved in exponential time. So we never need double exponential time, for example. Okay, so let's consider an arbitrary problem in NP. Let's call it pi. And so using the certificate-based definition of NP, we know now that there exists a polynomial P and a polynomial time verification algorithm V, such that, well, for every input that's in the language, so for every yes instance, there exists a certificate of polynomial length. So there exists a string C containing symbols among 0 and 1. The size of C is upper bounded by a polynomial in the input size, such that the verifier V returns 1 when it's given X and C. This Y should be C. And now for every input that's not in our language, so for every no instance, and for every string C, we know that the verifier returns 0. So because for no instance, there exists no valid certificate. Okay. So what remains to be done is that we just need to be able to generate these certificates. But since their length is upper bounded by a polynomial in x, in the size of x, we know that there's not too many of them. So, okay, so our exponential time algorithm will work as follows. So we will enumerate each string C that contains symbols 0 and 1, and that has length at most p of the size of x. Now we evaluate this certificate on this input instance using the verifier, and now we return yes if the verifier returned 1. And after having checked all these strings of size at most p of x, and none of these certificates was a valid certificate for the input, then we can return no. So the running time is 2 to the p of the size of x times the polynomial, because the verifier wants in polynomial time. And so this is exponential again. It's not doubly exponential, it's just exponential because we can upper bound it by 2 to the order twice p of x, which is 2 to the order p of x. But of course, again, this is not a constructive proof because we don't know what this p of x is. We know that these certificates exist, but we don't necessarily know, if we're given just an abstract problem pi in NP, we don't know what this polynomial is. And even for a specific problem pi that we are given, we might not easily be able to find out whether certificates of size x to the power 4 are enough or x to the power 5, and we actually might not know when we are able to stop. So, but the proof is still a valid proof because we know that p of x exists. And so we know that exponential time algorithms exist for each problem pi in NP, but we might not know what the actual algorithm is. Okay, let's talk about reductions, specifically polynomial time reductions. So we say that a language L1 can be reduced in polynomial time to a language L2, and we write this as follows. So L1 is smaller or equal, and then we have this subscript p here for polynomial time, L2. If there exists a polynomial time computable function, f, that goes from symbols in our alphabet to a set of symbols in the alphabet, such that for all input instances of L1, so x is a yes instance, if and only if f of x is a yes instance for L2. Okay, and now a polynomial time algorithm that computes this function f, so f is polynomial time computable, that's a reduction algorithm. Okay, so what does it do? So it takes an instance for L1, and this reduction algorithm does some computation, and it outputs an instance for L2, and that instance for L2 must be yes instance of L2 if and only if the input was a yes instance for L1. If it was actually given a no instance for L1, it also needs to produce a no instance for L2. So yes instances for L1 get mapped to yes instances for L2, and no's for L1 get mapped to no's for L2. Okay, so here's one way how we can use these reductions. So we can actually use the reductions to solve new problems. So let's say we have a solver for L2, and the solver is a polynomial time algorithm for L2. Okay, so now we're wondering whether some word x is in L1. Okay, so what we can do is now we can use the reduction. So our reduction, it gets this word of L1, so it does some computation, and out comes a word for L2. And so this is in L2 if and only if x is in L1. So, and our reduction works in polynomial time, right? So we have that f of x is in L2 if and only if x is in L1. So what we can do now is we can take this f of x, we can feed it to our solver, and if the solver says f of x is a yes instance for L2, then we know that x is a yes instance for L1. If the solver says that f of x is a no instance for L2, then we know that x is a no instance for L1. So we can solve the L1 decision problem. Okay, let's define NP-completeness. So first of all, we need to define NP hardness, and we will say that the language L is NP hard if L prime can be reduced in polynomial time to L for every language L prime that belongs to NP. So every language L prime in NP can be reduced in polynomial time to L So if that's the case, then we say that L is NP-hard. And so this means that, well, L is at least as hard as any language in NP because of this polynomial time reduction. So if we had a solver for L, then using the polynomial time reduction, we could then also solve L prime using the reduction together with the solver. Okay, so L is at least as hard as any language in NP. Okay, what does NP-complete mean now? Well, a language is NP-complete if it belongs to NP and it is NP-hard. So, okay, so here we have NP. It contains P. It contains NP-C, so the set of NP-complete problems. And now the NP-hard problems, they contain, those are those problems. So they contain everything in NP-complete, but also problems that are outside of NP. So NP-complete is the intersection of NP and NP-hard. Okay, one of the first NP-complete problems was CNF set. So this was proved in the 70s. It was proved that CNF set is NP-complete. And this was done by encoding the acceptance problem for non-deterministic Turing machines into the CNF satisfiability problem. So, and since very smart people already gave us one problem that's NP-complete, now we can use this to prove that other problems are NP-complete. So, if L is a language such that there's a polynomial reduction from some problem L prime to L, and this problem L prime is NP-complete, then we can conclude that L is NP-hard. If, in addition, L is in NP, then L is NP-complete. So we know that for every problem L double prime in NP, there exists a reduction from L double prime to L prime because of the definition of NP-completeness. And since we also have that L prime can be reduced to L in polynomial time by transitivity, well, by combining the two reductions together into one reduction that still takes polynomial time, we have that L double prime can be reduced to L for every L double prime in NP. And therefore, L is NP-hard, since every problem in NP can be reduced to it. Okay, this is the most important slide of the lecture. How do we prove NP-completeness? Well, so there's two things we need to do to show that the language is NP-complete. First of all, we need to prove that it's in NP, and we can use the certificate-based definition for this. So we can prove that there exists a polynomial certificate such that, well, if a valid certificate exists, then this shows that the problem is yes instance, and if no valid certificate exists, then it's a no instance. And this often results very easily from the problem definition. So if the problem is to look for an assignment that satisfies some properties, then the assignments will be the potential certificates. Second, we need to prove that L is NP-hard. And to prove that L is NP-hard, we need to select a language, L prime, that we know is NP-complete. So L prime needs to be NP-complete, and now we describe an algorithm that does the reduction. So it maps every instance of L prime to an equivalent instance of L. And then we can prove that X is a yes instance for L prime if and only if applying the reduction gives us a yes instance for L, for every input instance. And so we just need to prove then that the algorithm that computes F once in polynomial time. So the one very important thing here is that we need to do the reduction the right way around. So we want to prove that some problem is NP hard. We select a known NP-complete language, L prime, and then reduce from L prime to L. So input instances for L prime need to be translated to input instances for L, and of course we need to get equivalent instances. So a yes instance for L prime gets mapped to a yes instance for L, and a no instance for L prime gets mapped to a no instance for L.